Hello and welcome back to Chapter 9. We're still dealing with sequences, series, and probability, and today we're going to look at Section 9.6 that deals specifically with counting principles. We are going to start off with an example today, and that example says, to determine the number of ways a computer can randomly generate two integers from 1 to 12 whose sum is 6. Let's go ahead and list them out. The first row is going to be the first number that's drawn. The second row is going to represent the second number that was drawn. Now, if I draw a number 1, that means my second draw is going to be a 5. If the computer draws a number 2 to get a sum of 6, that would mean that we'd have to draw a 4 for the second number. If the computer draws a 3 for the first number, then it must also draw a 3 for the second number. If a 4 is drawn, then the second draw must be a 2, and if a 5 is drawn, the second draw must be a 1. So when I go through and I count the number of ways that I can generate two integers between 1 and 12, whose sum is 6, I have 1, 2, 3, 4, 5 different possibilities. So I get 5 different ways that I can do this. Now example 2 says, to determine the number of ways a computer can randomly generate two distinct integers from 1 to 12 whose sum is 10. Now distinct means that I have to have two different numbers that are drawn. I can't have the same number as we did in example 1 with the number 3. So I'm again going to list these out. I'm going to have the first number that's drawn and the second number that's drawn. And when we list these out, I see that if I draw a 1 first, then the second draw must be a 9. If I have a 2, then the second draw is an 8. If I draw a 3, the second number is 7. We can draw a 4 on the first draw and have a 6 for the second draw. I cannot draw the number 5 because the only possibility then would be another 5, and I need distinct integers. So we're going to skip over 5 and jump to the next possibility. So if I draw a number 6, then my second draw has to be a 4. My first one, if it's a 7, that means my second draw is a 3. If the first draw is an 8, the second draw is a 2. If the first draw is a 9, then that means the second draw must be a 1. And again, if I go and I count, I see that I have 1, 2, 3, 4, 5, 6, 7, 8 distinct ways, or 8 integers from 1 to 12 whose sum is 10. Now if you go back and look at example 1, we say that example 1 occurs with what we call with replacement. Okay, and the reason I know it was with replacement because when I got to the term where I drew a number 3 for the first number, I was also able to draw a number 3 for the second draw. Now, example 2 was an example of a situation that occurs without replacement. In other words, I wasn't able to draw a number 5 on the first draw and then turn around and draw a 5 on the second draw because that would have meant that I would have had to have put that number 5 back into the computer-generated system. Now in examples 1 and 2, it was easy to list out the different possibilities. However, as the number of occurrences increases, this is not always a feasible option. So when this happens, we want to use what we call the fundamental counting principle. And the fundamental counting principle states that if we have event 1, which is represented by capital E, and event 2, if these are two events, the first event, E sub 1, occurs in M1 different ways. After this event has occurred, then the second event can occur in a second amount of ways. So the number of the ways that the two events can occur is found by calculating the product of M1 times M2, or the number of ways that event 1 can occur times the number of different ways M2 can occur. Or, I'm sorry, event 2 can occur. Now, this pattern will hold true if we have 3 or more events. The only difference is I would be going M1 times M2 times M3 and so on. So with example 3, it says a combination lock will open when the right choice of 3 numbers from 1 to 30 is selected. How many different lock combinations are possible? Now, what our fundamental principle just stated was that I need to look at how many times M1 occurs. And if I have the numbers from 1 to 30, I know that I have 30 possibilities. Now, when I come up with that second number in the combination, I again have the option of going from 1 to 30 to pick out a number. So I again have 30 possibilities. And the number of possibilities for the third combination number is still from the range of 1 to 30, or a possibility of 30 different numbers. So to calculate the number of different lock combinations that are possible, I'm going to go 30 times 30 times 30, and if you multiply this out, this is 27,000 different combinations that can come from a padlock with 30 numbers on it in a combination of 3 numbers. Another similar example is like one of example 4 that says in a particular state, each autoplate consists of 2 letters followed by a 4-digit number. How many distinct license plate numbers can be formed? Well, let's just kind of draw a little scenario here. I know that the first spot on that license plate is going to be a letter. The second spot on that license plate is going to be a letter. And then it says it's followed by 4 numbers. Okay, and it doesn't give me any limitations on the letters or numbers that can be used. So I'm going to assume that my letters are from A to Z and my numbers are from 0 to 9. So when I look at this first letter, I know that there are 26 letters possible. When I look at my second letter, again, I can use any letter, so I still have 26 letters. When I get to my numbers, I have all the numbers from 0 to 9, which is 10. No restrictions on what my second number can be, so I also have 10. My third number, I have the possibility of 10 different numbers. And the fourth number is also a possibility of 10 different numbers. So if I take all of these numbers and multiply them, 26 times 26 times 10 times 10 times 10 times 10, this is going to give me 6,760,000 different license plate combinations. When dealing with counting principles, we have to look at 2 different situations. And the first one is called permutation. This deals with the ordering of the events, and with permutation, order matters. That's the number one thing that you have to keep in mind, is that order does matter. So when we look at example 5, it says, in how many ways can 8 children be lined up in a row? Well, in this case, if you think about it, order matters. Once I select one of those children, that child is no longer able to be selected for another position. So I'm going to, when I go to select that first child, I have 8 children to choose from. When I go to select the second child, I now have 7 children to choose from. When I go to get to the third spot, I've got 6 children to choose from. When I select my fourth child, I now have 5 children to choose from. And this is going to continue on. So the 5th spot means I have 4 children left. The 6th spot means I have 3. 7th spot means that there are 2 children left. And then when I get down to the 8th child, there's just 1 left. So if I use the fundamental counting principle, I'm going to take each one of these events and multiply them together. So I end up with 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is really equal to 8 factorial, if you remember from the previous section, an 8 factorial then is equal to 40,320 different ways that I can rearrange these 8 children. So when order matters, and we're using permutations, the number of permutations of n events can be found by taking the number of events n and making it factorial. Example 6 says, a coin club has 5 members. In how many ways can a president and vice president be selected from its members? So if I have my president here and my vice president here, to figure out the number of presidents I have, or that I can choose from, is 5, since I have 5 members. Now once that president has been selected, I now have 4 remaining members that can be selected for vice president. So to find out the number of different ways that we can select a president and vice president, I'm going to multiply the two together, or get 20 different ways that we can select a president and vice president. Now sometimes it's relevant to order a subset of a collection of data versus doing the entire set of data. So this is called the permutation of n elements taken r at a time. And this is given by the formula that you see right here. Okay, and the n represents the number of data sets that you have, and r is the number that you are actually looking at. So let's go ahead and look at our next example. If we look back at example 6, we had 5 members to choose from when we were selecting our president and vice president. Now I only had 2 spots that could be filled. So because order mattered, I'm going to use permutations, and I'm going to use the NPR setup. So if I go in and I plug in my n and r, my r values, I know that n was the total number that I had to select from, which was 5, p, and then my r is the number of spots that were available, or 2. So to solve this, I can plug that into n factorial, which becomes 5 factorial, divided by 5 minus 2 factorial, and this gives me 5 factorial divided by 3 factorial, which is also equal to 20. Okay, and you can either use a formula, or if you recall on your calculators, if you go to the math function, arrow all the way over to the probability section, and there's a button, I believe it's number 2 or 3, that has this NPR notation right here in there that you can also use. And I can help you with that one once we get back to class. Now sometimes when we're looking at sets of data, we want to know what a distinguishable permutation is. And a distinguishable permutation is defined as a set of n objects that has n sub 1 of one kind of an object, n sub 2 of a second kind of an object, n sub 3 of a third kind of an object. Okay, in other words, if I have a set of data, let's look at, we'll just go 1, 1, 1, 3, and 5. N sub 1 would be these 3 ones here. N sub 2 would be all of the number 3s. N sub 3 would be all of the number 5s, and so on. So what I'm going to do with that is I still have 5 total terms here, which is going to represent my n, but those 5 terms are comprised by adding up all of the individual, the fact that I have 3 1s, 1 3, and 1 5. So when we want to find the number of distinguishable permutations, we can find that by taking the total number of terms n factorial and dividing that by the product of the number of individual terms factorial. And we're going to do an example here. Example 7 says to find the number of distinguishable permutations of the following group of letters. We have AA, EEE, J, PP, and R. So to calculate this, we're going to use the equation that we were just given. And I see that I have 9 total numbers. So that 9 is going to go in the numerator as 9 factorial, and I'm going to divide that by the number of a's that I have, which I have 2 a's, so I'm going to go 2 factorial times, I see I have 3 e's, so I'm going to go 3 factorial, times 1 j, and that's going to be 1 factorial, times 2 p's, or 2 factorial, and 1 r, so that will be 1 factorial. Again, this 2 came from my a's, the 3 came from my e's, the 1 came from my j, this 2 came from my p's, and the 1 came from the r's. So when you solve this, you end up with 60,480 in the numerator divided by 4, which simplifies to 15,120 distinguishable permutations. Now, we are up to the point where we're going to look at a second type of counting principle called combinations, and with combination, order is not important. So if I give you this set of letters, A, B, and C, technically with combinations, because order does not matter, I could rewrite that as B, A, C, and because both of them consist of an A, B value, and a C value, and it doesn't matter what order, they are both equal. So this is what combinations mean, is order does not matter. So example 8 says, in how many different ways can 2 letters be chosen from the letter group A, B, C, D, E, F, G, when we know that order is not important? So we can go ahead and list them. I know that I can have A and B, A and C, A and D, A and E, A and F, or A and G. I can then go B and C, B and D, B and E, B and F, B and G, or C and D, because C has already been paired with B and A in the previous 2 columns. So I have C and D, C and E, C and F, C and G. Then I can look at D. D's already been paired with A, B, and C, so we can start with D and E, D and F, and D and G. E has already been paired with A, B, C, and D, so then I just have E and F, and E and G. And F has already been paired with A, B, C, D, and E, so that leaves us with just F and G. Now if you go through and you count all of these, there's 1, 2, 3, 4, 5, 6 in this row, 1, 2, 3, 4, 5 in the next column, 1, 2, 3, 4 in the next column, 3 in this column, 2 in this column, and 1 in this column. So if you add all of these up, 6 plus 5 plus 4 plus 3 plus 2 plus 1, this gives us 21 different ways that we can combine the 2 letters chosen from letters from A through G. Again, it's not always feasible to sit there and list out every different combination that there is, so it's nice to have a formula to use. When we're looking at combinations of n elements taken r at a time, we can use this equation right here. And it's the number of elements of combinations taken r at a time is equal to n factorial divided by the quantity of n minus r factorial times r factorial. Now, if you notice, this piece right here should look familiar. And it looks familiar because it's really the same thing as our permutation formula. So another way to calculate this would be to take your permutations and divide that by your r factorial value. So for example 9, it says, for an experiment, 4 students are randomly selected from a class of 20. How many different groups of 4 students are possible? So we're going to ask ourselves right away, does it matter the order of the students? And in this case, it doesn't. So because it does not matter, I know that I'm going to use combinations. And to use combinations, the only other thing I need is the number of my total sample and then how many positions I'm looking to pull from that sample. So in this case, there were 20 students total, and I'm going to be taking 4 at a time out of there. So if I go 20C4, okay, and again, this is a function in your calculator underneath that probability function or tab underneath math, you get 4,845 different groups that can be formed out of these 20 students. Our last example says that you are forming a 10-person committee from 9 women and 12 men. The committee must consist of 5 women and 5 men. How many 10-member committees are possible? This example, even though order doesn't matter because it doesn't matter which 5 of the 9 women we're going to take or which 5 of the 12 men we're going to take, we do have to treat it as 2 separate instances though. I have the men scenario I have to look at, and then we have the women scenario we have to look at. So let's go ahead and treat these as we have the women and then we have the men. Because order doesn't matter, we have to use combinations. And with the women, I have a total of 9 women, and I'm going to be pulling 5 of them out. So when I solve that, I see that I have 126 different possibilities. And for the men, we have a total of 12 men, and we're pulling 5 of them out. So this gives me 792 different possibilities. Now because I have 2 separate events here, and I want to know how many committees I can form, I need to multiply the 126 by the 792, and this gives me 99,792 different 10-member committees that are possible. Now, to kind of wrap things up, we need to kind of look at the important pieces for counting principles. The first thing you need to do is you need to determine right away whether or not order is important. If order is important, then you have to know that you have to use the permutations. If order doesn't matter, then you need to sit there and think, okay, that's got to be combinations. Then, the third thing we need to look at is whether or not the problem involves 2 or more separate events, kind of like our example 10. Okay, if it involves 2 or more separate events, then we're also going to have to incorporate the fundamental counting principle as well. And now for today's fun fact. Today's fun fact deals with the phrase, getting one's goat. And this is a fact that I got from the book titled I Didn't Know That by Carlin Evans. And it says, it was common practice in the early days of horse racing to place a goat in the stall with a high-strung pacer to calm him before the race. The two made good roommates, but before long, it also became common practice for an opponent to steal his competitor's goat in order to upset the horse before the race. Many good racehorses were ruined by someone, quote-unquote, getting his goat. Now don't let anyone get your goat, and I hope you have a great evening, and we'll see you in class tomorrow. Thanks, and have a good night.